Hello, physics students. We are on Chapter 9. So in Chapter 9, we shift gears some. We are going to tackle another big topic in physics. We've done kinematics, we've done dynamics, all about Newton's laws and motion and all that stuff. From Chapter 9 and 10, we're going to get into a big topic called, I guess we'll just call it work and energy. Looking at physics from a perspective not just of motion and forces, but of work and energy. There's a big work-energy theorem that kind of is a holistic approach to physics that we're going to look at. There are at least three kinds of work that we're going to look at in this class. They are three kinds of energy. Kinetic energy, that's the energy of movement. Potential energy, that's the energy of position, like just the fact that something is far above the earth gives it more potential energy than something that's just sitting on the surface. Or a spring that is coiled has more energy than a spring that is just in equilibrium, more potential energy. And the other one is thermal energy. That's the energy of interactions due to heat. That's kind of an internal energy that we're going to talk about also. All right, this is kind of a very good picture to think about what energy is happening here. All right, the bow and the arrow and the string, if we think about that as a system, there's a lot of potential there. We call that a potential energy. When he lets the string go, the arrow starts to fly. That potential energy converts into the energy of movement called kinetic energy. So in Chapter 9, we're going to be mostly focused on kinetic energy and how that relates to work. All right. How should we think about energy? Chapters 9 and 10 will develop the basic energy model, powerful set of ideas using energy. A key distinction is between the system, which has energy, and the environment. Energy can be transferred between the system and the environment, or transformed, in other words, converted between one kind of another within the system. Some important forms of energy are potential energy associated with an object's position. There's a good illustration of that. And kinetic energy associated with an object's motion. And then thermal energy is the energy of the random motion of atoms within an object. All right, the units for energy is called joules, and we'll talk about that. What joules are made of as far as the SI basic units that make up a joule. Process that changes the energy of a system by mechanical means, pushing or pulling on it, is called work. So work changes the energy of a system by mechanical means. Work, the symbol W, is done when a force pushes or pulls a particle through some displacement, thus changing the particle's kinetic energy. All right, so some force is applied to this particle and moves it through some displacement. And by doing that, it is changing the particle's kinetic energy, and thus it is doing work, according to the definition of work in physics. What laws govern energy? Working with energy is very much like accounting. A system's energy, we will just give it the symbol capital E, changes by the amount of work done on the system. The mathematical statement of this idea is called the energy principle. And here it is, the delta E of the system, in other words, the change in energy of the system is going to always equal the amount of external work done on that system. So something from the environment, some outside thing, something outside of the system does work on that system. And the amount of work done is going to always equal the change of energy within that system. So this diagram is kind of showing that. So this box represents the system. Everything inside the box is the system. Everything outside that box is the environment, or anything outside of the system. So this arrow represents work done on the system by the environment, and that increases the energy inside the system. This arrow here represents the system doing work on the environment, and that's energy going out of the system. It decreases the work in the system. Sorry, I meant to say it decreases the energy in the system. So actually that means that since work and energy equal each other, that means they have to have the same units. And they do. The energy for work and the energy for, the units for work and the units for energy are both the joules. All right, next, what is power? Power is the rate of doing work, or the rate of transforming or transferring energy. So it's not work and energy and power. Work and energy are synonymous, kinda. But power is not exactly synonymous. Power is a rate of change for energy, or a rate of change for work. Kind of like position and velocity. So for machines, power is the rate at which they do work. For electricity, power is the rate at which electric energy is transformed into heat. Or you could say the rate at which energy is used into heat, light, or sound. Power is measured in a different unit called watts. And it's very related to the joule. A watt is 1 joule per second. All right, so a 100-watt light bulb will use energy faster than a 60-watt light bulb. And for that reason, it will be brighter and cost more money. All right, why is energy important? Energy is one of the most important concepts in science, engineering, and society. Some would say it is the most important. All life depends on energy, transformed from solar energy to chemical energy to us. Society depends on energy, from industry and transportation to heating and cooling our buildings. Using energy wisely and efficiently is a key concern of the 21st century. All right, let's see if we can answer the reading questions, even though we might not have read. Maybe the intro helps us answer these. The statement delta K for the system equals the external work is called the what? So remember we just looked at something in the intro that said delta E equals external work. K is a certain kind of E. It's kinetic energy. So instead of just energy in general, this is just being more specific. The change in kinetic energy in the system equals the external work done on that system, and that's called the what? Let's see here. That is called the energy principle. All right. Kinetic energy. What is kinetic energy? You don't know this yet, but it is 1/2 times the mass times the speed squared. All right, so in other words, the energy of movement depends on the mass of what is being moved, the mass of what is moving, and it also depends on how fast that mass is moving. In fact, it depends more on the speed than it does the mass, because the speed is squared, whereas the mass is not. But it depends on both.
What did you say then?
All right, the transfer of energy to a system by the application of a force is called what? Well, that's what work is. That's called work. All right, a vector C has magnitude C. So this is the vector symbol. This is just a numerical quantity. Then the dot product of the vector with itself is, we have not talked about what a dot product is yet, but it is C squared. So it's kind of what you would expect, like C times C is C squared. But there's more to it than that. We'll talk about it later. Hooke's law describes the force of actually springs. So Hooke's law is a law that's dealing with the energy or the movement or of a spring. We'll talk about that later also. The work done by a dissipative force like friction is always what? It's always negative. So that's what that's when if you think of a car as the system and everything outside of the car as the environment, when you slam on brakes, the kinetic energy of that car is decreasing, and it's decreasing because that car is doing work on the environment, or you could say the environment is doing negative work on the car, and that's because of the friction that is bringing that car to a halt. It's the interaction between the system and the environment. And that's called a dissipative force. Friction is a dissipative force for a system. It's always negative work. Light bulbs are typically rated in terms of their watts. The watt is a measure of what? Watt is a measure of power. Okay. Energy overview. Everyone has some sense of what energy means. Moving objects have energy. Energy is the ability to make things happen. Energy is associated with heat and electricity. We're constantly told to conserve it. Living organisms need it. Engineers harness it to do useful things. Some scientists consider the law of conservation of energy to be the most important of all the laws of nature. Kinetic energy. K. Kinetic energy is the energy of motion. All moving objects have kinetic energy. The more massive an object is, or the faster it moves, the larger its kinetic energy. Potential energy. So kinetic energy had the symbol K. You would think potential energy would have the symbol P, but it doesn't. It has the symbol U. Capital U is a symbol that refers to potential energy. And it is the energy, it's a stored energy that is associated with an object's position. So this roller coaster at the top of its path up here has the most potential energy it's going to have in the path we can see in this picture. The roller coaster's gravitational potential energy depends on its position. It depends on its height above the ground. Thermal energy. So the symbol for that doesn't have any kind of special symbol. It's just E with a subscript TH. So ETH, E sub TH, is thermal energy. Thermal energy is the sum of the microscopic kinetic and potential energies of all of the atoms and bonds that make up an object. So if we think of I would think of kinetic energy and potential energy as an external energy. Energy that is an object is doing, outside, that affects the outside of the object. That's kind of the thermal energy is all of that stuff going on within an object, inside of an object, like what the atoms are doing inside of that object. The farther they are away from each other, or the faster they're moving, the more thermal energy that object has. So as this horseshoe, in other words, as this horseshoe heats up, the atoms in that horseshoe they're getting farther away from each other. So it's increasing their potential energy with one another, and they're also or they're moving faster. And that's really what heat is. An object has more thermal energy when it is hot than when it is cold. That's why when you heat up an object, almost all objects, when you heat them up, expand. All right, the system and the environment. Within a system, energy can be transformed from one type to another. So you might have heard in physical science, there's a law of energy or matter, and we should say matter and energy, that matter and energy, we should say it out like this: matter and energy can neither be created nor destroyed, but they can be transformed into each other or into different types. All right, as long as the system is not interacting with the environment, the total energy of the system is unchanged. A process that transfers energy to or from a system by mechanical means is called work. A process that transfers energy to or from a system by thermal means is called heat. All right, so when energy is transferred by thermal means, it's called heat. So here's energy in the system. The system has an energy, we just call it E sys. That's the energy of the system. And it's got kinetic, thermal, potential, and chemical. We don't talk about chemical energy in this class very much. And they can all transform into the other types. The energy can also transfer into the system by the environment or into the environment by the system. And that would be called the external work done. All right, putting a shot. The system, if we call the system the shot, that's the sphere, the heavy sphere here. Transfer. The work done by this athlete on that sphere is going to be all transferred into the kinetic energy that sphere will take on, which is the movement of that sphere. The athlete is the environment, and it does work on pushing the shot to give it kinetic energy. Pulling a slingshot. All right. In this case, the work done by this hand on this slingshot is not, the whole slingshot system itself is not moving, but what it has given it is the ability to change into kinetic a lot of kinetic energy without any more extra work being done on it. So it has given it what's called potential energy. So the buoy is the environment. It does work on the slingshot by stretching the rubber band to give it potential energy. Falling diver system. The diver and the earth. So in this case, the diver is not the system. The diver and the earth are the system. And you could define that either way. Sometimes, it just depends on the situation which one is more advantageous. But according to this example, the diver and the earth both are within the system as defined by this example. So what's happening here is that the potential energy, the fact that the diver and the earth are farther from each other, and there's an attractional force called gravity between them, that means there's a transfer going on inside the system, not outside the system. Transfer, because the earth is part of the system, from potential energy to kinetic energy. Now, if you just consider the diver as the system, and the earth was outside of it, then it would not be a transformation of energy. It would be a transference of energy. The energy would the environment, which is the gravitational force of the earth, would be doing work on the system, which is the diver, giving it energy it didn't have before, giving it kinetic energy that it did not have before. But if we define it as the earth and the diver, then it's all potential energy that is being transformed, not transforming into kinetic energy. So there's different ways to assess and analyze these situations. Speeding meteor. The meteor and the air. So I guess we would consider this meteor coming into our coming into our atmosphere. Then I guess we could consider the meteor and the air both as all part of the system. In that case, the kinetic energy of the meteor would be all transforming into thermal energy because of all the drag and friction that's going on between the meteor and the air. If you just considered the meteor to be the system, then the air would be outside the system and would be doing work on that system. So then it would be a transference of energy instead of just a transformation of energy. The system would be changing its level of energy because of the work being done on it. But here, if the air is part of the system, then it's not a transference. It's not that the energy in the system is changing its value. It's that it's changing its type. It's changing from one kind to another. But the total value would not be changing. The meteor and the air get hot enough to glow as the meteor's kinetic energy is transformed into thermal energy. The energy principle. Transformations of energy within a system move the energy around but don't change the total energy of the system. Change occurs only when there's a transfer of energy between the system and the environment. So it totally depends on how you define the system. If we treat incoming energy as a positive transfer and outgoing energy as a negative transfer, and with work being the only energy transfer process that we could consider for now, we can write it like this. That the change in the energy of the system, so how much the energy increases or how much the energy decreases, is always going to equal the work done on that system by something outside of that system, the external work. All right. This is called the energy principle. All right, here's a basic energy model. Notice we don't have chemical energy in here because we're not going to talk about that much in this class. That's for a different class. So the types of energy inside of the system are kinetic, potential, and thermal. And again, energy going into the system, that's energy, that is work being done on the system by the environment. That's a positive value for work. Out here, this is work being done by the system on the environment. So like, think of the car slamming on brakes, and those brakes, the tires are undergoing friction with the ground, and so the ground itself is also going to be heated up by that. If you define it that way, then the energy is coming out of the system, going into the environment, and that would be a negative value for work. But if you considered the ground as part of the system, then there would be no change in the total energy of the system. You would just say it's all a transformation from kinetic to thermal in that case. So the thermal energy would rise, the kinetic energy would fall, and it would be by the same amount. So the total energy of the system would remain the same. So the energy of an isolated system, one that does not interact with its environment, so there's nothing external happening, that's called an isolated system. If that's the case, then we say that energy is conserved. That is the only time we can say that is the law of conservation of energy. It only applies to an isolated system, a system in which there are no external factors, there are no external actions, interactions with that system. All right. Model fails if there is energy transfer via thermal processes, heat. All right, quick check 9.1. This is a very tricky question. Skier is gliding down a slope at a constant speed. What energy transformation is taking place? Notice it says transformation, not transference. There's no transfer of energy between the system and the environment. There's only transformation taking place, which that clues us in to the fact that for this example, we are going to consider the skier and the earth as one system, all part of the system. So the earth is not part of the environment and the skier is the system, and the earth is doing work on the skier. That's not the case for the way this is being set up. This is going to be set up as the earth and the skier are both a part of the system. So the skier is gliding down a slope at a constant speed. The fact that the skier is going at a constant speed means that there is no change in kinetic energy, because the skier's got this. Kinetic energy is 1/2 mass times velocity squared. So there's no change in the mass of the skier. There's no change in the velocity of the skier. Constant speed. So it's not going to be kinetic energy changing into anything. The fact that the skier is skiing down a slope means the skier's position relative to the earth is changing. So potential energy is changing into something. That potential energy is not changing into kinetic energy, again, because there's no change in kinetic energy happening. What's happening is that gravity down the slope and friction up the slope are canceling each other out because it's a constant speed. And when there's friction, there's going to be heat happening. That's kind of what happens with skiing. Friction between the skis and the snow causes the snow to melt some. That's kind of what makes the skis have very little friction anyway. So what's going on then? The potential energy is transforming into thermal energy, and that's what's a little bit of heat that's melting that snow as you go. That's a very tricky question. Working energy for a single particle. Consider one particle acted on by one constant force that acts parallel to the direction of motion, pushing or pulling on the particle as it undergoes a displacement delta S. All right, that's a very simple situation. Force is happening to the right. The particle is moving to the right in the same direction, and it goes a distance delta S. We define the particle to be the system while the agent of the force is in the environment. Okay, so that's how it's being defined here. The figure shows both an interaction diagram and a before and after representation. So here's the interaction diagram. Here's the before and after representation. So the force is acting on this particle, giving it this velocity. And notice that the velocity vector is greater after that happens, at the end of that distance. And the distance that it goes is delta S. We can define a new quantity called the kinetic energy of the particle. K equals 1/2 mv squared. K depends on the particle's mass and speed, but not on its position. For the case in which a single constant force acts on a single particle, K changes in direct proportion to the distance traveled. So the SI unit of K is given its own name, the joule, and here is the breakdown of what the joule is in SI units. It's 1 kilogram mass times meters squared per second squared, or meters per second quantity squared. That is velocity squared. So it's mass times velocity squared. So kilograms times meters squared per second squared. Quick check 9.2. Ball A has half the mass and 8 times the kinetic energy of ball B. So then what must be the speed ratio VA to VB? All right, that's going to be doing a little bit of math here. All right, that's let's say 8 times the kinetic energy of ball B. So let's say K for A equals 8 times the K for B. And we know K is 1/2 mv squared, so 1/2 the mass of A times the velocity of A squared equals 8 times 1/2 times the mass of B times the velocity of B squared. And what else do we know? Ball A has half the mass of ball B. So MA is half of MB. So I'm going to substitute this in for MA to have one less variable in there. So 1/2 times 1/2 MB VA squared equals 8. Let me go ahead and say that's just 4 MB VB squared. All right. So this is 1/4 MB VA squared equals 4 MB VB squared. I can go ahead and cancel the MB's. If I divide both sides by that term, they can both cancel out. Let's multiply both sides by 4. Cancel that out. So now I've got VA squared equals 16 VB squared. And we're looking for the ratio of VA over VB. So if I divide both sides by VB squared, so I got VA squared over VB squared equals 16. Take the square root of both sides. That gives me VA over VB equals 4. 4. All right, hopefully you were able to follow all that. You may have even been smart enough to be able to do that without having to do all that math, but I kind of had to do all that math. All right, so I'm going to say it's choice B. And it is. All right, the work done on a one-particle system causes the system's kinetic energy to change. The change in kinetic energy, in other words, the final kinetic energy minus the initial kinetic energy, is equal to the amount of work done by an external force. Should say WEXT. For the case of a constant force parallel to the direction of motion, in other words, down the S-axis, whatever that is, X or Y or Z or whatever, the work is an integral. All right, calculus. So work is the integral of force over a distance. So not with regard to time, but with regard to a displacement, with regard to a distance. And if the force is constant, you could bring that force outside of the integral, just integrate with respect to ds. And so what that gives us, if we do that integral, the integral of ds is just s. It's like a constant, it's a constant 1, do the power rule, you just get s. And you plug in the final position and the initial position, and you just get, it's the force times the change in position. Force times the final position minus the initial position. All right, the unit for work is the same as for the energy, which is the joule. Let's make sure that makes sense. So it's newtons, like force is newtons. That's kilograms times meters per second squared, because F equals ma, times, this is a distance, so that's meters. That gives us kilograms times meters squared per second squared. So again, it works out to the same base SI units, and those make up what we call the joule. All right. So F delta S, that's the simple way to do work. When you wouldn't be able to do this, when you would actually have to do the integral, is when the function for S is something that's kind of a strange mathematical function that has to be integrated instead of just being some nice constant. All right. Work can be either positive or negative. If the force causes the particle to speed up, then the work done by that force is positive. Negative work means that the force is causing the object to slow down and lose kinetic energy. So that's go back to the example of the car slamming on brakes. And obviously that car is losing kinetic energy, it's getting slower. The sign of W is determined by the force direction and the displacement direction. So when the force direction and the displacement direction are the same, so the force points this way and the object moves this way, then that's going to be positive work. All right. Or when the force points to the left and the displacement is to the left, that's also positive work. It's only when the force points in a different direction from the displacement that we have negative work. So if the force points to the left and the displacement to the right, then that force is actually doing negative work on that object. It's slowing it down. Or vice versa, if the force points to the right and the displacement points to the left. Notice this, it says work is 0 if the particle doesn't move. In other words, if there is no displacement, then that force is not doing any work on that object. All right, work done by a constant force. A force F acts with a constant strength and in a constant direction as a particle moves along a straight line through a displacement, which we're going to call delta R in this case. So you have this force vector happening, but the object is going through this displacement vector, so the force is not exactly in the direction of the motion. That's also not opposite of it. So what you can do here is just break it down into its component that is in that same direction. So just take this component of that force. So the force, the component of that force, and you could do that by just doing some trig. It would be F cosine of theta. That would give you that, and so that's the only part of that force that is actually making that object move in that direction of displacement. So that's the only component of that force that's doing any work on that object. So it would be F cosine theta times delta R or delta S or whatever that position variable is. The work done by this force is what we've said before. It's the integral of the force in the S direction, ds, which is the magnitude of the force times cosine of the angle, ds. And this is constant, so it comes outside of the integral. Notice we're not integrating with respect to theta. We're integrating with respect to s, which is why F cosine theta. Theta is not a variable here, okay? It's a constant. That whole thing can come outside of the integral, and we just integrate with respect to s, which again just becomes this constant times the final position minus the initial position, which just simplifies down to that. All right, here notice that theta is defined as the angle that F, the force vector, makes with the delta R vector. All right, example 9.2, a strap inclined upward at a 45-degree angle pulls a suitcase 100 meters through the airport. The tension in the strap is 20 newtons. How much work does the tension force do on the suitcase? All right, so if we just say, here's the force, the tension force, and it is 20 newtons. And this thing undergoes a displacement of 100 meters. So that's delta R. So it's not that full tension that's doing work. Some of that tension is actually counteracting gravity. Only this component of that tension is doing that work. This is a 45-degree angle. So doing a little bit of trig, it's that tension force times the cosine of 45 times that delta R. That's going to give us the work done by the force on that suitcase. So this is 20 times 100 times cosine 45. So that's going to be 2,000 times root 2 over 2, which is 1,000 root 2. And root 2 is 1.41. So if we wanted it as a decimal, 1410 should be that, around that many joules. So that's what it says right here also. It rounded to a different decimal place, but that is the same answer. All right, quick check 9.3. A crane lowers a girder into place at constant speed. Consider the work W sub G done by gravity and the work W sub T done by the tension cable. Which is true? All right, so this object moves from here to here. Okay, delta R. Tension points this way. Gravity points this way. So the fact that, and delta R is this way, the fact that tension is opposite direction of the displacement means that tension is actually doing negative work. So the work done by tension is less than zero. Gravity points in the same direction as the displacement, and so gravity is doing the positive work on this. And so gravity, the work of gravity is greater than zero. So what is looks like choice B. Yep. Right, here you can read over this tactics box if you want to. And you can read over this tactics box if you want to. And you can read over this one. All right, quick check 9.4. Robert pushes the box to the left at a constant speed. In doing so, Robert does positive, negative, or zero work on the box. All right, because Robert is pushing the box and the box is moving, he is doing work, and it's moving in the same direction as his pushing, so he's doing positive work. All right, 9.5, quick check. A constant force F pushes a particle through a displacement delta R. In which of these three cases does the force do negative work? All right, choice A, choice B, choice C, choice D, or choice E. Okay, here the force is, so the force is not, if we think about it like this, this is the component of force that is doing any work on that. And so it's pointing in the opposite direction of delta R. So A is definitely doing negative work. Here, the force is also, this is the component of the force doing work that is pointing in the opposite direction of the delta R. So this one's also doing negative work. Here, the force is pointing in the same direction as R. So that's positive work. So I'm going to say choice D. And it is. All right, example 9.3, launching a rocket. A 150,000 kilogram rocket is launched straight up. The rocket motor generates a thrust of 4 times 10 to the 6 newtons. What is the rocket's speed at a height of 500 meters? All right, before this chapter, we would have done this as a free body diagram. We would have that force of thrust, all right, and we would have had this force of gravity, and we would have figured out the net force, or the sum of the forces. The y direction would give us something, and it would be equal to MA, and we'd figure out what A is based on that. And then once we found A, we would then go to kinematics. All right, so I can't spell right now, but you get my picture. We would then, once we get A, we'd do kinematic equations to try to figure out the answer to this problem. The energy paradigm that we're learning now gives us another way to analyze these problems. We can do it according to work and energy. So work, let's say the work done by the motor is equal to the force of the motor times, let's just say delta y. In this case, delta R, we'll just say delta y because it's going up and down. There's also work. What other force is acting on that rocket in that direction? Gravity. That's the force of gravity. Also times delta y. But at this time, the force of gravity is pointing in the opposite direction. It's pointing down from delta y because the rocket is moving upward. So that's going to be a negative work. So that's going to be 4 times 10 to the 6th times delta y, which is 500. And that's going to give me 20, 0, 0, and then 6 more zeros. It's a bunch. Let's just say times 10 to the 6th. All right. Well, we could write that as 2 times 10 to the 9th. Work done by gravity is, what is the force of gravity? It's the mg. It's 150,000 times 9.8. And then times delta y also, which is 500. All right, we're going to make this be negative because it's pointing opposite direction of the displacement. That is 7.35 times 10 to the 36, 10 to the 8th. So the network is going to be 2 times 10 to the 9th minus 7.35 times 10 to the 8th. Let's see what that is. I get 1.265 times 10 to the 9th. That's the net work, and so that is the total work done on that rocket. The external work is equal to the change in energy, which in this case is all a kinetic energy change, or equals the change in kinetic energy. So that's going to be so 1.265 times 10 to the 9th equals 1/2 m VF squared minus 1/2 m VI squared. I could just factor out the 1/2 m, and if I do that, then it just becomes VF minus VI, both of them being squared. And so this is equal to 1/2 times 150,000 times, and VI, because it starts at rest, is 0. So VF squared, and I can just solve for V. So let's see what happens when I do that. So 1.265 times 10 to the 9th divided by 1/2, in other words, times 2. And then divided by 150,000, and then the square root, $129.9 meters per second. So that's again, we could have done it multiple ways, and that's the power of physics. It holds consistently with those different paradigms that we use. All right, so here you can look through this. It's what the book shows in the slides of how it could be done. And they get the same answer, 130 meters per second, which is what we got. All right, slide 60. Which force below does the most work? All three displacements are the same. Okay, so notice it says sine 60 is 0.87, cosine 60 is 0.5. All right. So the delta R is the same in all cases. So the work, remember work is equal to force times cosine of theta times delta R. So in this case, the delta R is the same for each one, so don't even worry about that. So then what is F cosine theta for each one of these? Well, here, theta is 90 degrees, and cosine of 90 is 0. So this 10 Newton force right here is doing 0 work. It's not doing anything to move it that direction. All right, what about the 8 Newton force? It's going to be 8 cosine of 60, which is 8 times 0.5, which is 4. This is 4 joules of work. And then this 6 Newton force is 6 cosine of 0. Well, cosine of 0 is 1, so 6 times 1, that 6 Newton force is doing all of its work in that direction. So 6 is greater than 8 cosine 60, so the 6 Newton force is doing the most work. All right, a light plastic cart and a heavy steel cart are both pushed with the same force for a distance of 1 meter. Starting from rest, after the force is removed, the kinetic energy of the light plastic cart is going to be what compared to that of the heavy steel cart? All right, it's both undergoing the same amount of work, because work is the force times the distance. And they both have the same force and they both have the same distance. So the same amount of work is being done on both of them. And if the same amount of work is done, and if we set the work equal to the net kinetic energy, then for the top one, it's going to be 1/2 mv squared. And for the bottom one, it's going to be equal to 1/2 mv squared. But for the bottom one, the top one is a smaller m. Therefore, it's got to be a bigger v squared to make up for that, to make up for that difference. Here, it's a bigger m, so it's got to be a smaller v squared to make up for that difference. So this one is going to be a greater velocity than this one when the same amount of work is done on both of them, and that makes sense because if you do the same amount of work on something of less mass, it's going to do more to it. It's going to give it greater velocity. All right, but as far as the kinetic energy is concerned, so we can say this one has the greater velocity, greater v squared. But as far as the kinetic energy is concerned, the work done is equal to the kinetic energy, and so it's the same amount of work on both. So it's going to be the same amount of kinetic energy given to both of them. So that's going to be equal to the kinetic energy of the light cart is equal to the kinetic energy of the heavy steel cart. I think I'm going to stop it there and call this part 1 for chapter 9. See you again in part 2.